Welcome to this presentation on time to failure estimation brought to you by MotorDoc LLC. In this presentation, we'll discuss the importance of proper PDM technology selection and how the frequency of testing can be applied. We'll also discuss how to use the P to F curve to put your program together and how you can provide risk of failure assessments associated with the application of predictive maintenance. MotorDoc is a consulting and service company that provides support in developing programs, implementation, and data collection and analysis for virtually all industries. Services also include forensic analysis of electric machine system failure, troubleshooting, root cause failure analysis, specification development, repair shop review, and witness testing through the repair process. Contact us with any questions. Full details at the end of this presentation. The following concepts can be applied on any machine. A common myth is that a machine with a redundancy is not critical because a ready spare is available. We're going to explore this question from the standpoint of the reliability function. The P to F curve can be used along with the knowledge of failure modes in order to select the correct on-condition analysis and inspection methods. Finally, a quick and dirty method of determining the risk of failure, time to failure estimation, and impact of the failure can be determined using the reliability function. More strenuous methods are also available, but outside the scope of this presentation. The first topic is the redundancy myth, where inexperienced analysts or consultants make the claim that a system does not have to be maintained because it has redundancies or a backup. In reality, the addition of each redundant system will improve the risk of failure just a little more than without a redundancy. There are three primary reasons for installing redundancies. First, to improve, not guarantee reliability. Second, to improve or provide additional capacity. And finally, to allow for maintenance to be performed on the equipment by switching over to the redundant equipment. To understand the reliability function, we must understand a few concepts. These include the mean time between failure, or MTBF, which is the time frame divided by the number of failures, the mean time to repair, or MTTR, the failure rate, and repair rate, which are the number of repairs or failures per unit of time. For instance, if we have a 20 horsepower pump motors operating at 1750 RPM and in 40,000 hours of operation, each motor fails 3 times, then the MTBF would be 40,000 hours divided by 3, or 13,333 hours. The failure rate, or lambda, would be 1 over 13,333, or 7.5 times 10 to the negative 5th power. The information can be put into the reliability function, which is the natural log of the negative time times the lambda, or failure rate. By looking at a series of times, a curve can be drawn that represents the survivability of the equipment over time. For instance, with the information previously discussed, we can see that in this instance, the equipment has a 37.7% chance of operating at 40,000 or 13,000 hours. The reliability function can be applied to series and parallel systems as noted. In series reliability, the first calculated reliability finding times the next one, and so on. This can be used to calculate the survivability of a complete series system. In parallel reliability, there are two methods. In the first one, two identical systems are calculated by adding the first two systems and subtracting the two systems multiplied together. In more than two identical parallel systems, the reliability is 1 minus the product of 1 minus the finding to the nth power. When you have redundant systems, as they are added, the reliability improves but never reaches 100%. Using the graph above, at 13,000 hours, the survival of the system is approximately 40% for one motor, 63% for two motors in parallel, and 79% for three motors in parallel. As you will note, the reliability does not double for each parallel system. This means that for critical systems, even if they are in parallel, they must be considered critical in the RCM and FMEA process. The P to F curve can be an excellent tool to select the right test or inspection for on-condition analysis of the motor system. In effect, it can provide a grading system that can be used to determine which technology or inspection should be selected. For instance, in the case of a motor bearing, the bearing was installed new and remains relatively reliable over time. At some point, wear, material defects, maintenance, contamination, shaft currents, and/or other forces cause a bearing to begin to fail. As a bearing transitions from good to failed, the bearing temperature begins to rise and vibration begins to increase. If monitoring with vibration, there is a point at which alert thresholds will be passed and the condition can be detected accurately, or point P. From that point, there's a period of time until the bearing actually fails, or point F. The minimum vibration root frequency to detect this problem should be 1/2 of the time between points P and points F or greater. For a given threshold, for a given bearing fault detection technology, vibration in this case, adjusting the alert thresholds can increase or decrease the P to F slightly. So it's a good idea to compare technologies considering the ability to detect a fault and how early. This allows the analyst to determine if the optimum solution and the optimum frequency of inspection is acceptable. So, for instance, if we take this case where we are comparing vibration to ultrasound, based upon the experience of the users, the accuracy of the instruments, and the history or best guess, it is determined that the vibration can detect most bearing faults 3 months before failure in ultrasonics, 6 weeks before. That would end up with a minimum inspection frequency of 6 weeks for vibration and 3 weeks for ultrasonics. It still must be noted that this is based upon the MTBF for the bearing failure. Some will fail sooner, some later, and some very quickly and may still not be detected. Therefore, the more critical the application, the more frequently testing should be performed. How to determine how many inspections is beyond the scope of this presentation. We'll cover it later on. Since a majority of failures are random, risk of failure always exists. A majority of these random failures are not instantaneous, but can be detected in advance with properly selected tests and inspections. For critical equipment, it is important to be able to estimate the time to failure so that the impact or what the impact should be if the equipment should fail. There are a number of methods to determine, with varying degrees of accuracy, an estimate of the time to failure for a complete component or system. The accuracy varies depending upon such things as the reliance upon the method of the analyst's experience and instinct up to detailed studies of the types of components or systems. A few of these methods include simulation methods, what-if scenarios, and Weibull analysis. For this presentation, we'll discuss one of the more quick and dirty methods for quick determination of time to failure estimation. Without detailed studies, the analyst can rely upon history, records, or experience to determine the chance of survival using the reliability function. For instance, if a bearing fault is detected and it is known that the MTTR after fault detection is about 5 weeks of 24/7 operation before the bearing seizes, a modified reliability function can be used. Using history, the severity of the bearing problem, and experience, the analyst determines that the bearing stands about a 75% chance of operating at the time that it is tested. The MTTR from this point is about 840 hours. When the numbers are plugged in to the modified reliability function, it can be determined that there is about a 30% chance of survival at 840 hours. Putting this curve into action, we can now begin to answer the question that is often asked: will the machine last until the next shutdown? Say, for instance, the next shutdown is in 6 weeks or 1,000 hours of operation. We can present the response that, based upon our assumptions, the bearing has a 23% chance of surviving to that shutdown. This both provides risk-based information to decision makers and also sends the message that if the bearing survives beyond the historical 840 hours, that you are not incorrect. Instead, the bearing just beat the odds. The impact of these concepts can be tremendous. What if we need to determine if a system can operate 24/7 for the entire year, skipping a shutdown? We're building a case for the application of machine monitoring, diagnostics, and management has made the decision that maintenance is not required because the machine does not fail that much. We look back at the history of the machine components from the control to the load and determine the following. The motor starter has failed once every 15,000 hours. The motor has a good history and has failed every 25,000 hours. The coupling fails every 12,000 hours, and the driven load fails every 20,000 hours. With the probability of survival without maintenance being 12.2% in the first year, 1.5% in the second year, and 0.2% in the third year, the decision is not really valid. The method provides a clear-cut, unemotional method of demonstrating why maintenance is important, and it is found in the very basic principles of industrial engineering. This approach, as well as a few others, can help the maintenance department focus on specific areas, help determine how to maximize maintenance efforts, and help communicate the risk of reduced maintenance. We'll be discussing details of how this can be achieved later on. Now we will discuss how to bring this all together. The concept of time to failure estimation, or TTFE, is the ability to estimate the chance of failure over time following fault detection. It is used to provide a risk-based tool for prioritization of repairs and other reliability decisions. Originally developed using basic industrial engineering principles and studies on motor circuit analysis, the concept has been extended to include all industrial systems. In this case, we're going to discuss a simple approach to selecting the minimum test frequencies to get the optimal benefit of the TTFE program utilizing the standard P/F curve. To understand the concept of TTFE and condition-based maintenance testing and inspections, we must understand that there are different failure characteristics for the different systems. The charts shown here represent a system's chance of failure over time. For instance, the traditional bathtub curve has a high instance of failure when the system is first installed that drops to a random failure until it eventually wears out. The wear-out curve, until considered normal by most people, involves a random chance for failure until the equipment simply wears out. The random failure curve means that from when a system is first installed and through its life cycle, it maintains the same chance for failure. In a number of studies of systems since 1968, it has been determined that the most likely type of chance of failure in any complex system is random failure. Prior to the 1980s, the most common type was the infant mortality random failure, with the bathtub curve actually relating to a human life from the 1920s and not machinery. After that time, the most likely was random failure from the time of installation. However, the most common failure curves overall are the random failure curves, as very few systems have age-related failures. There are two versions of the standard P/F curve. One is a logarithmic curve that relates to most random failure systems, and the second is a straight line that relates to most wear-out systems. The objective is to try to determine what the chance is along the P/F curve. As the one on the left is the most common, the formula that is simplest to use is the modified availability formula, as shown and discussed previously. In the meantime, however, we can use this curve in order to select the optimal test or inspection for condition-based maintenance. In this example, we might consider the ability to detect winding faults for a specific application. For winding shorts, MCA may be able to detect the particular issue earlier than surge testing and both well ahead of insulation resistance testing. Using this tool, the analyst can determine which method would be best for the application with an optimal frequency of testing, which would be half the time difference of the point of detection till the system fails. Through a review of a particular fan system, the following issues were determined to have occurred historically. In the distribution system, loose transformer and bus connections. In the motor control center, loose connections and poor contacts. The motor has had bearing problems and winding shorts. The coupling system has had worn sheaves and belts as well as tensioning and alignment issues. The fan has had bearing problems. This may be an individual fan system or a set of fan systems. Through an understanding of options, inspections, and technologies available, as well as the average time of the P to F with each method, optimal solutions can be determined. With the ability to detect the transformer and bus connections approximately 6 months out, infrared can be selected to be performed at half of 6 months or quarterly. For motor control center connection problems, infrared can be used quarterly. With contacts, an inspection of the contacts can detect problems 6 months out, but in this case, it also requires an intrusive maintenance practice. An alternate method is a voltage drop test performed every 6 weeks. With the motor bearings, vibration performed every 6 weeks would be the best option. However, if there are a large number of systems fed off a single MCC, the solution may be different. Winding shorts require MCA performed every 6 weeks. With the belts and sheaves, vibration is selected. However, as mentioned earlier, if there are a number of systems, it may be more effective to use electrical signature analysis from the MCC to detect the issue. Finally, the fan bearings should require vibration every 6 weeks. The result of this analysis is infrared performed on the electrical systems quarterly, a voltage drop test performed on the starter every 6 weeks, vibration and MCA is performed on the motor and fan every 6 weeks. Thank you for watching our presentation. For more information on this topic or MotorDoc services, please contact us via email at info@motordoc.com.